Hello and good morning. My name is Daniel Miles, and in this video, we'll be covering controlled channel attacks, deterministic side channels for untrusted operating systems. This is a research paper uh, written by Zhuangzhang Chu and also featuring Marcus Pinato and White Q, and was submitted during the IEEE 2015 symposium. Before we get into the definition and the meaning behind the title I just shared, let's lay down some groundwork. It's a pretty safe assumption to state that most applications that are developed in a way such that the operating system is considered and assumed to be benign. In other words, is considered to be a trusted resource. We don't typically expect a threat to come directly from the operating system itself. This assumption, however, is starting to change. As new technologies become available, malicious attackers are continuing to leverage new techniques. They're continuing to innovate and try to circumvent and come up with new ways of getting to unprotected data. This is making the question of, should I consider an operating system malicious, or is my operating system malicious, more of a valid concern? The idea of a malicious operating system can be manifested and realized in several different ways, but some examples could be, say, a operating system like a cloud OS that is offered as a service, but that is offered from a shady or malicious company, or a benign operating system that has been compromised and potentially redistributed by a hacker. Well, if malicious operating systems are becoming more of a concern, are there any countermeasures against these malicious operating systems or any solutions that are in place to help protect vulnerable applications? And yes, there are. These are called shielding systems, and they do exist and they help address the problem. Shielding systems can come in a number of different flavors, but typically they exist between the operating system and the application and work as a bit of a middleman. So they protect the application and prevent any sensitive information or private information that the application is running from bubbling up to the operating system. And at the same time, they abstract the needed services that the application requests from the operating system, such that the operating system does not have to interact with the application directly. This helps to mitigate the risk of a malicious operating system pulling information from the application, since it has to go through this shielding system, this kind of extra layer of protection. This is done in such a way such that the operating system can still provide critical services to the application while the application's sensitive data stays protected. Along with protecting the application from potentially malicious operating systems, the shielding system existing as a brand new layer between the two is a benefit in and of itself. What this allows is it allows for the protection to reside separate from the application that's running or the operating system that the application is running on. This is a benefit for protection in both ways. One, we don't have to spend extra development time and money retrofitting an application to work with the shielding system. We can use the application that already works. And we also do not have to require access to the operating system and make modifications there, when most times, especially if this is a malicious operating system, we may not have access to that. What this allows is allows for the application and the operating system to still work together while the application is still protected without requiring modifications to either. Most shielding systems work with requiring little to no modifications of either the application or the operating system. And in those cases, we refer to them as legacy applications or legacy operating systems. So, sounds good, right? Problem solved. Well, this presentation wouldn't exist if there wasn't at least some problem with the situation. So, what's the catch? The catch is that despite the protections that shielding systems offer for the application, there are some ways of circumventing this and still getting at the private sensitive information that the application is holding. We call these methods side channels, and this presentation is going to go over one such side channel attack that can be successful at uncovering private information, specifically in the context of a legacy application that is running on a malicious legacy operating system while the application is being protected by a shielding system. Unfortunately, that means our application is still vulnerable. So let's look into how this attack works, maybe find out how it can be implemented, and see if there's anything we can do in order to protect against it. To start off, let's approach this from the attacker's perspective. Though the operating system is malicious, the application still relies on the critical services that the operating system offers. These can be storage, access to a network, memory management, etc. And the attacker can make use of this dependency. One such service that the operating system offers is memory management. And through this, the operating system controls paging, how big the pages are, and the access to those pages, as well as handling any page faults that might happen during the application's runtime. The shielding system still offers some protection, as the shielding system sits between the application and the operating system and intercepts these page faults and relays the information to the operating system in a way that does not expose the application's known state or does not expose the sensitive data contained within. However, the presence of a page fault itself offers the attacker some useful information. The attack begins with the attacker having to do some homework on their target application. If the target application is an open source application, then the attacker already has easy access to the source code and can use this to perform analysis as well as construct a more efficient attack. However, even in the event that the attacker does not have access to the source code, the attacker can still perform analysis on the binary of the target application directly. This is a more time-consuming task, but it is still very much so a doable one. Through this analysis, the attacker can become more familiar with the functions and data accesses that the application would make use of. And the attacker can make use of an additional fact, and that is that the functions called and the data that is accessed will tend to be different provided that the input to the program is different. To put this in another way, a unique input tends to yield a unique pattern of function calls and data accesses, and the attacker can leverage this in order to find out important information about the application. Let's say we were to look at the application and the flow of control transfers and data accesses that happen during runtime. We can look at individual points in the code that would result in branching paths as being of one of two categories, either input-dependent control transfers or input-dependent data accesses. Both of these categories work on the same premise, the premise being that input A results in one behavior while input B results in the other, except the difference is that for control transfers, we have a transfer of control, meaning a function A or a function B is being called. And for data accesses, we have different data that is being accessed, either data A or data B. This means that the next step for the attacker in pulling sensitive private information from the application is the ability to detect these input-dependent, either control transfers or data accesses. Let's start with control transfers. Recall earlier that we assumed the attacker either has access to the source code of their target application or has done extensive binary analysis of that target application. What this means is that the attacker would have access to the code that's being run and know how the application is structured. So with that, let's consider a small coding example. Here we can see that we have a function foo that has a conditional statement in which function A will be called on one condition and function B will be called on the other. The condition is the value of grade in the test1 object of student, and if it is greater than or equal to 80, pass student will be called, and if it is less than 80, fail student will be called. If the operating system is somehow able to manage to detect when pass student or fail student is called during runtime, then the operating system can in turn understand information about the student object, specifically about the value of grade during runtime as well. Though the operating system does not have direct access to the application during runtime, it can still detect when these functions are being called. Since the operating system is still in charge of memory management and page access, the attacker can leverage this in order to detect function calls. If the memory is paged such that pass student resides on one page, say page 7, and fail student resides on another, page 8, then the operating system can restrict access to these pages. When the application goes to run the function on those pages and realizes it does not have access to that page, it will trigger a page fault. And which page triggers the fault will tell the operating system which function is currently being called. If the question of how many students passed test 1 is important, then the attacker can find this information simply by counting the number of times page 7 had a page fault. But wait, the page fault only tells us which page triggered the page fault, not necessarily which function on that page. A single page can contain multiple functions and data objects. So is this method of detection infeasible? Is this page level granularity too coarse to be useful for detection? If so, then our application is protected. Our data is safe. But unfortunately, that is not the case. It's true that the page fault only tells us that a function on the page triggered the page fault, not necessarily which function on the page. But we can expand our previous method to account for this. If we expanded our page manipulation to include the foo method itself, such that foo, pass student, and fail student all reside on separate pages, then when the application goes to call pass student, it will trigger multiple page faults during the process, one for foo, and then one again for either pass student or fail student. This creates a sequence of page faults that is unique for each function that needs to be called. And it's this unique pattern of page faults that can be used to identify the specific function. So, despite having a detection method that works only at the page level, the operating system is still capable of detecting whether a specific function is called at runtime. And from this, it can infer secret application information. Our application data is not safe. One category down, one to go. Let's look into how the attacker can detect input-dependent data accesses. Using a similar method as before, the attacker can make use of page faults in order to glean important information from the application. Let's consider the code snippet above. Here, students is an array with student ID being an index used to pull specific student information. If students is an array that spans multiple memory pages, then we can use page faults in order to determine whether or not student ID was within a certain range. In this example, whether student ID was less than or equal to 6 or greater than 6. We've now showcased how an attacker can pull private application information via a side channel such as page faults. Let's now recap the requirements for such an attack to be feasible. The target application must run on a vulnerable operating system, either maliciously coded or compromised by a hacker. The operating system must be capable of manipulating memory page access. Most modern operating systems do this. And the source code of the target application is needed for offline analysis, or the binary of that target application can be used for binary analysis. This is used for planning malicious paging, discovering function paths, and creating a more effective attack. Provided the previous requirements are met, the attacker has access to the sensitive application data, and current shielding systems struggle to mitigate this risk. As an example of some of the data that can be pulled out via this attack mechanism debuted at the 36th IEEE Symposium with Wangxiang Zhu as the speaker. There he stated that this attack was successfully carried out in a test environment during which they were capable of reconstructing images used by an application using libjpeg library. They managed to recover the entire novel of The Wizard of Oz that was being spell checked via Hunspell with a 96% accuracy. And they managed to recover text with 100% accuracy of any English input passed through FreeType for font rendering. This also included punctuations. This is pretty impressive and very effective. From an attacker's perspective, this is awesome. But from a user perspective, it's a bit disheartening. How do we stop it? Well, at the time of the paper, which was written in 2015, the options were rather slim. The legacy application could be rewritten to better hide the access of data flow or function calls, but this could require a lot of time and effort, as well as incur additional costs due to more development. So on the other hand, we could try and fix it via the shielding system by imposing more stringent restrictions on the operating system. But this also has its drawbacks, as imposing restrictions on the operating system could also affect the functionality and those critical services that the underlying application requires. I also did some searching to see if any new solutions to this problem have come up, and unfortunately I was unable to find any work towards a solution with the context of shielding systems protecting legacy applications from malicious legacy operating systems. In conclusion, this type of side channel attack, specifically a controlled side channel attack, since the operating system has control over the side channel, continues to be a threat, as it can be very successful in pulling private application data. This threat increases with time as cloud computing becomes more popular and is easily accessible, and shady companies, malicious service providers, or avid hackers could utilize such attacks to pull important data from the user applications that they host. In short, this topic is worthy of more research, as work towards a solution is needed. Thank you.